Hello everybody, welcome back to another Gregorious Maths video. In this video, as I said, I would be not just making one video in this short period of time, which I like to call the weekend. I am further progressing through algebraic geometry, and today I'm going to be talking about rational curves and what that means for a curve to be rational. I'm going to talk about a little bit at the end about a field theoretic perspective, although I won't go too much into that. There's more detail in the book about that I'm going to go into, just because some of the field theoretic stuff at the end does get used throughout the book, and so it's just a nice excuse to introduce that notation, and also a nice perspective to take. Rational curves. So again, we're looking at algebraic plane curves, but we're going to be looking at a certain class of them, and yeah, we're going to be looking at what they are and a couple of applications of them, actually, mostly relating to calculus, and we're going to look at how rational curves relate to Euler substitutions of all things. I should note that I am currently typing up a blog post about solutions to exercises of section 1, and I haven't done any of the exercises yet, but I will be typing up my solutions as I do them, and so I will make a quick community post for every blog post with the answers to the exercises, or at least my answers. So obviously they might not be completely correct or whatever, but you know, I think that's quite neat too, to keep the blog active as well. Anyway, let's talk about rational curves now. And to start off with, we'll look at the following curve. That is y squared is equal to x squared plus x cubed. Okay, so let's just take a quick look at what this actually looks like. If you go onto Desmos, you'll see that the curve looks something. I mean, that's a terrible drawing, of course. I might even just like put up a picture of a actual version of it on Desmos, but this is roughly the shape. It has this weird little thing in the center, it goes through the origin, and then there's two lines coming off of it. And so basically the observation is that for a ray, y equals tx, it will pass through, if we have a ray, y equals tx, it will pass through the origin, so it will intersect there, and if you keep going, it will eventually pass through another point of the curve. So it intersects it in two places, and obviously even for negative gradients like that, it will also intersect the curve in two places. And again, I'll show this on Desmos, and hopefully I'll edit over this, but basically y equals tx will intersect this curve in two places. And so what we're actually going to do is we're going to parameterize this curve, which is a notion from multivariable calculus. And the idea is that, you know, all of these curves, so we want to find the grade. You know what, I'll explain it afterwards. So let's just parameterize this curve, and then we'll talk about the intuition, and yeah, hopefully I can get some things on Desmos, maybe, you know, that'll help me explain. Anyhow, so y equals tx. Let's plug that in there, shall we? So then we get tx squared. Okay, let's just move everything to one side. So we'll get x squared plus x cubed minus t squared x squared is equal to 0. And so we factor out our x squared. So we get x squared times 1 plus x minus t squared equals 0. And so the double root at x equals 0 is the origin. So where else does this thing intersect? When else does this hold? That is when x is not equal to 0. When else does this hold? And in fact it's when 1 plus x minus t squared is equal to 0, or that is x squared is equal to t squared, x is equal to t squared minus 1. If we rearrange it, if we have x plus 1 plus t squared equals 0, then we get x is equal to, sorry, minus t squared. We have x is equal to t squared minus 1. Okay, so if x is equal to t squared minus 1, then y is equal to t times t squared minus 1. And so our parameterization is actually y equals t times t squared minus 1, and x is equal to t squared minus 1. That's our parameterization, and you'll notice that if you put this for y in here, and this for x in here, and you rearrange it, it will always be equal to 0. That is, t squared minus 1 all squared, plus t squared minus 1 all cubed, minus t times t squared minus 1 all cubed will always be equal to 0. That's just an identity for all t. And so this leads us, and actually the geometric meaning of t is also quite straightforward. What t is, okay, let me draw this picture but bigger actually, let me draw this nice and big, in red. So, okay, if we have our curve which is looking something like that, then our t, again this is really hard to draw because I want it to intersect the line, but so go through the origin, because they always will, so if we actually like draw it like this, because it will never be parallel, so if it goes to the origin, again it's hard to draw, but basically what t is the gradient of the line which connects the origin to another point on the curve. That's what t is in this parameterization. And hopefully, yeah, I'll have a nice Desmos thing to show you there. Here's the Desmos that I was promising. After my abysmal drawing, you can see what the curve actually looks like in red, and that as t varies, the line y equals tx always intersects the curve at the origin and at another point. But, more importantly, this leads us to the following natural definition. The fact that this is always, if we plug that in, that's always equal to 0. We have a definition, an algebraic plane curve, which I don't think it's normally abbreviated to APC, but just for laziness, I will denote it by APC. An algebraic plane curve is rational if there exist rational functions phi and psi such that f of phi of t, psi of t is equal to 0 as an identity for all t. And so this has quite a few applications, just quick applications. Firstly, if we have a value, if we plug in t0, if we have some t0 in some subfield k0 of our function of what it's defined on, if we have t0 in that subfield, that means that this actually also will be, that means that phi of t and psi of t will also be in that subfield k0. And so what this means is, for example, if we run t through rational values, we're actually getting all of the rational points on this curve here, for example. And in fact, another application lies in integral calculus, of all things, because if we have a rational function that we would like to integrate, so if we have the indefinite integral of g of xy with respect to x, we can actually make this into elementary functions by doing the following, by just substituting in and doing the necessary stuff. So this is equal to the integral of g of phi of t psi of t times, I think it's phi prime t dt, which is again in terms of elementary functions, and that's nice. So okay, let's give a couple of examples now of such rational curves. Lines, for example, algebraic plane curves of degree 1, they're obviously rational. And it turns out that all conics are also rational. And I can't recall exactly, because you can construct, for any conic, you can construct the exact rational functions which you need to put in. But I can't recall how to do that, although what I do recall is that as an application of that, using this fact here, if we have y squared is equal to ax squared plus bx plus c, then we can, then when we do the following technique, we get that the integral g of x root ax squared plus bx plus c dx is equal to, can be reformulated, and this application of the parameterization is actually just Euler substitutions. And so Euler substitutions is kind of like an application of this rational parameterization, which is quite cool, because that's quite a nice technique for integration. So okay, that's all I have to say about rational curves and their a couple of examples. A good question which you could be asking yourself right now is, how do we know when a curve is rational? And unfortunately, right now, I don't have an answer to that, because I don't have the necessary tools in algebraic geometry to answer that right now. Apparently it's a delicate question, which requires much more algebraic geometric machinery, and so I'm guessing that that question has been answered, and actually I will look this up after the video. I'm guessing the question has been answered. You know, you can kind of give certain conditions for when a curve must be rational, but you know, it requires a lot more advanced algebraic geometry, so I won't go into that now. So as promised, I will be talking about the theoretic side of things now. And that is, we make rational curves over some algebraic plane curve x into a field k of x. And what it is the set of also u of xy, where these are points on the curve, equal to p of x y over q of xy, and and mod the equivalence relation that p of xy over q of xy is equal to p1 of xy, and of course none of these are divisible by f, so this denominator is not divisible by f, where f is our algebraic plane curve, is equivalent to p1 over q of xy, if and only if we have that p1 of xy times q of xy plus, actually no, I believe it's minus p of xy q1 of xy is divisible by f. It's divisible by f. So that's how we make it into field, and you can check that it's a field with the obvious multiplication and addition. And okay, so I'm just going to introduce a couple more definitions, but not just because they will be needed later on. Firstly, note that this rational curve might have more than one representation. So, for example, on the circle, x squared plus y squared is equal to 1, we can... Okay, actually, no. Yeah, okay, so we could have two different representations. We could have, say, for example, 1 minus y over x, or we could say, for example, have x over 1 plus y. And at the point, yeah, at the point 0, 1, this thing is going to die, but this thing is going to be completely fine. And so this representation here is regular at 0, 1. Because, okay, we said that u is regular at p if u of p... the denominator of u of p does not vanish at 0. At p, sorry. That's what regularity is. And, what was I going to say? U of p is regular, u is regular at p if the thing does not vanish. And, oh god, I completely forgot what I was going to say. But that is pretty much all of the definitions and stuff that I did want to introduce anyway. And so yeah, thank you guys for watching. I find this application to integral calculus quite cool, just because I didn't expect that to happen. And ready for next time, because next time we'll be looking at rational maps, which are a generalization of rational curves. And then finally, not finally, but then I'll be looking at more stuff about the projective plane and singular points and stuff like that. And hopefully by the time that I've done those videos, I will have done a pretty complete blog post full of exercises and solutions, nearly ready for publishing. Anyway, thank you for watching, and yeah, I'll see you in the next video, which will hopefully be very soon. So yeah, have a good day, and yeah, goodbye, blah blah blah, bye.